Hello students, this is Chintan Patel and welcome back to the video lecture series of the fundamentals of machine design. In this lecture, we are going to look at the Castigliano's theorem and strain energy for different loads. So basically this theorem is a part of the beam section, or whatever we have seen in this entire chapter is related to columns or struts that we call in our example as well as in our theories. So what we are going to see, what we are about to see in this lecture is related to beam. This is the theory which can be asked in your examination within a 3, 4 or 5 or 7 marks, whatever the examiner is willing to ask. Basically, this theory is used for the determination of the deflection of the beam, which is one of the topic in our syllabus. So, deflection of the beam can be determined using the Castigliano's theorem. We will also see some applications of this theorem in the beams and in the upcoming slides. So, first of all, we will start with the basic theorem, in which we will see the basic background concept as well as the statement of the theorem and the equation of the theorem, which you need to write in your answer whenever it is asked in your examination. So first of all, you need to understand what is the strain energy whenever a body or a beam is subjected to a certain amount of the forces. So as you can see on the screen, when an elastic body is subjected to a force or a system of force, it deforms. That is natural. That is the nature of the body, that whenever a certain amount of the force beyond its inertia force is applied on the body, then the body tends to deform. The external work done by the forces is stored in the body as a strain energy. Now, the work which we are doing on the body, whatever the force that you are applying or some other agents are applying on the body, some amount of the work energy is applied on the body in order to deform it. Now, whenever the body deforms, certain energy which is used to deform the body is stored in the body. This type of energy is known as a strain energy. So basically, strain energy is the energy which will be stored in the body while deformation. Okay, so while deformation, strain is also generated, and strain can be calculated only whenever the body is going to deform, because strain is nothing but the deformation per unit length, and that is why whenever a body is deforming, then you can find out the value of the strain energy that has been stored in the body while this phenomenon. Now, this was the definition of the strain energy. Now we will see the Castigliano's theorem. So as you can see on the screen, the Castigliano's theorem states that when an elastic body is subjected to a system of forces, now there may be the one force or more than one forces, the deflection at any point and in any direction is equal to the partial derivative of the total strain energy with respect to a force at that point and acting in that direction. Now, as you can see from the statement, we can now understand that why we have learned the strain energy definition first. Because in order to calculate the value of the deflection that is occurring in your body, whatever the elastic body that we are considering, in our case we are considering the beam. But whatever the body it is, whatever its shape or any dimensions, the body, if it is subjected to a certain amount of the forces, certain values of the forces and the system of forces, then you need to do some partial derivation of the strain energy in order to calculate the value of the deflection of the beam in any direction. Now, how can we do this? We will understand it by some diagram, which is also shown on your screen right now. So, basically, we have considered a diagram of a beam, and as you can see, a beam is subjected to a system of forces where P1, P2, P3, and Pi number of forces are applied on the beam in order to deform it. Now, beams are meant to support this type of the forces. Beam are the supporting member, so there will be always a certain amount of the forces acting on the beam in this vertical downward direction. Now direction might be changed, but in most of the cases the direction of the forces will be always in a downward direction. So right now we have considered that general case of the beam in which P1, P2, P3 and up to Pi certain forces are applied on the beam in order to deform it. And as you can see, a dotted line of the beam shows the deformation of the beam, which is a curvature line. And if I may just put some annotation over here so that you guys can understand. So this is the deformation of the beam. This is the initial condition where a beam has not been deformed, or we can say that before the application of the forces, and after the application of the forces the beam is now deformed in this manner. So we have considered two different conditions before the application of the forces and after the application of the forces. So there are two different conditions. Now if I consider this first number of point, then as you can see the beam initially was over here at this position, and after the deflection the beam is in this position. The beam is in this position, and that is why we can consider that the deflection of the beam which has occurred is this much, and this much deflection has occurred at a point 1, which is represented by delta 1. Now if you consider point 2, the deflection at the point 2 is different from the deflection at the point 1 because of the position of the support. As you can see, the point 1 was nearer to the support, and point 2 is far more further away from the support, and that is why the point 2 is going to deform more as compared to the point 1. So this is the deflection at the point 2. Similarly, you can find out the deflection at different points which is represented by delta in your figure. Now our aim is to find out this deflection. Now in order to find out this deflection, we have an equation from which can be derived from the statement of the Castigliano's theorem itself, and that is delta 1. Delta 1 equals to delta u upon delta p1. Now how this equation has came, I would like to show you this origin of this equation from the statement itself. If you see, the statement indicates that if you want to calculate the value of the deflection in any direction at any point, let's say we want to calculate the deflection for the point number 1. So at that particular point, deflection delta 1 can be calculated. Deflection delta 1 can be calculated as partial derivative of the strain energy. Partial derivative of the strain energy with respect to the force at that point acting in that direction. So let's say at point 1 P1 force is applicable, P1 force is applied, then P1 force is going to be our variable with respect to which we are going to derivate, we are going to do some partial derivation of the strain energy. Now U is the symbol of representation of the same strain energy. So U is a total strain energy stored in the beam. So let's say if U is your strain energy, then according to statement, you can do some partial derivation of U with respect to force that is acting at that point 1. So P1 is acting at the point 1, and that is why you can directly do some partial derivation of the U with respect to P1, which is given as a del U by del P1. Now this was the first point deflection. Now if you want to calculate the deflection at the point 2, then you can simply write delta 2 as a delta U upon partial derivation with respect to the force which is acting at the point 2. Now at the point 2, the force which is acting is represented as a P2 force. So if you consider the P2 force, then the partial derivation must be done with respect to P2. So in your equation, you will have to write the value as a du by del U by del P2. And here the variable with respect to which you are going to do a partial derivation is P2. So this is how the partial derivation works. And similarly, if you want to calculate the deflection at the I point, then you will have to just replace the value of 2 to I. Let's say delta I is equals to delta U upon delta Pi. So this is how you are going to calculate the values of the deflection of the beam at a certain point. One more point I would like to add here. Let's say we have a point at which no forces are applied. no forces are applied, or this is the point where any force is not externally applied. So let's say this is our point. Let's say I am giving this point as a number 4, and if you want to calculate the value at the value of deflection at the 4, now we will represent it as a delta 4. So if you want to calculate the deflection at the 4 point, then as you can see, as there is no force is externally applied, we have but deflection is there due to the forces which are applied in the vicinity of the point 4. So if you want to calculate this much deflection, then you will have to assume that here is also one force is applied, and let's say from our assumption that this force is Q4, let's say Q4, this force is Q4. We are assuming that there is one force is applied from the external side, but this is our assumption. Practically, there is no force applied on the point number 4. But in order to calculate the value of the deflection, we are assuming that there is one force already there on the beam point 4, which is named as a Q4. So if you assume this Q4, then you can write the equation of the deflection using the Castigliano's theorem, and successively you will be able to calculate the value of deflection in your application. So this is how we are going to use this theorem in our practical life. Now we will see the application of the Castigliano's theorem. How is it applied in our engineering field? So Castigliano's theorem is used for the determination of the deflection of the simple members as well as the complex structure, which is nothing new. Already we have discussed this. It can be used for finding the reaction of indeterminate structure. Now, what are the indeterminate structure? The structure which you are aware to calculate in your examples are determinate structures. The structure which cannot be solved, which can the structure in which you cannot simply apply the equations of the engineering mechanics on the force equations and simple rules of the force in order to solve these examples are known as an indeterminate structure. For example, if we are talking about a body which is fixed on both ends, then and if you are applying a force at the middle of the body in this direction, then there will be the reaction on both the sides of the body as this body is fixed on both the ends. That is why the direction and the magnitude of the reaction on both the sides R1 and R2 both are unknown and which cannot be calculated using our basic rules, and that is why you will have to develop some relation in order to solve this type of reactions and which is not simple. The method is pretty complex, and that is why this type of structures are known as an indeterminate structure. So basically it can be used for finding the reaction of the indeterminate structures, and this theorem is useful for the calculation of the same. So now we will see other application, and the application is the same which I have already explained in the previous slide. That if there is no force is acting on the body, and if you want to calculate the deflection in that particular point, then you are going to consider a force which is imaginary, or we are going to assume a force Q which is going to act at the point 4 in order to calculate the deflection at that point. Now the deflection can be calculated using the theorem, Castigliano's theorem, using this equation, that is del U by del Q, and this is how you are going to solve the deflection problem. Now we will see the different type of the questions which can be asked in the under the title of the strain energy for the different loads. Now we are going to calculate the value of the strain energy, because as you can see the Castigliano's theorem will only work if you know the value of U. U is your strain energy. Then you will have to do some partial derivation with respect to the force which is acting at the point, and then you will be able to calculate the value of the deflection. So this is how you are going to calculate the deflection, but first you need to know how to calculate the strain energy for different type of the load. So basically we have considered the loads which can be asked in your examination as an axial load, torsional load and a bending moment. So first of all we are looking at the axial load. As you can see, the axial load diagram is represented on your screen, where a body is subjected to a axial tensile force. It could be compressive, but we have considered the tensile force just for the calculation and the theoretical purpose, so that you guys can understand, and later on you can apply the same principle in the case of the compressive load. So first of all, consider a force F which is acting on the body in the axial direction. The body itself is of the L length, and right now we have considered only small amount of the length which is represented as a dx. So for dx we are going to calculate the value of the strain energy, and later on we are going to integrate the value of the strain energy for the entire length. So this is how we are going to calculate the strain energy for this particular problem. So if you consider the dx, then strain energy statement of the Castigliano's theorem itself indicates that the body is an elastic, and that is why if the body is elastic, then the force which you are applying is going to proportional with the deflection, because under the elastic condition only this relation holds good. So if you draw a diagram, if you plot a diagram of the force versus deflection, so on this axis we are representing the force and on this axis we are representing the deflection. Then this diagram is only for the length dx. Then we can consider the strain energy stored in the length dx as a du. Now the strain energy which is stored in the body is one type of the work energy. So work can be calculated as a area under the PV diagram. Similarly, we can consider the strain energy, which is similar to the work, as a area under the F delta diagram. So this is one type of a work, and that is why we are going to use a similar concept to calculate the value of the strain energy. So as you can see, the area under the work F delta diagram is represented by a triangle. So if you can calculate the area of the triangle, then you will be able to calculate the value of the strain energy, that is du for the dx length, small length. So as you can see, the area of the triangle can be written as a one by half base into altitude. So base is delta, d delta, and altitude is force F, whichever we have applied, we have considered. Okay, so if you want to calculate this delta, then we also have an equation for this particular delta, that is PL upon A. So instead of the P, we have represented here as an F. L is our length, and we have considered only dx length for this particular strip or an element, and AE is the common cross section area and the elastic constant based on the material. So we are going to put this equation into the above equation so that we can have a broader view of the delta du. So if you can consider du after the simplification will give you the answer as a f square dx upon 2ae. So this is the strain energy for the dx length. Now we need a strain energy for the entire length of the L. So in order to calculate the strain energy for the entire length L, what are we going to do is we are going to integrate the above equation for the from 0 to L. So as you can see, the integration from 0 to L du, and if you put the value of the du in this equation, then your total strain energy would look like this. We will leave this equation. We are not going to solve this equation further. So this is the purpose of this type of a derivation is just to let the examiner know that you know the concept how to calculate the strain energy. And if it is asked in your examination, then you can calculate the strain energy using the simplification of this equation. So basically, we will leave our topic over here, which is the strain energy for the axial load. Similarly, we are going to look at another topic, that is the strain energy for the torsional load. So if you consider the torsional load, then torsional load is similar to the axial load. The only difference is that the axial load is going to deform the body in a transverse direction or in the longitudinal direction. But torsional load is going to deform the body in an angular direction, because it is going to change the dimension in an angular direction, so it is going to twist the body. So that is only the change. And now in order to twist the body, the only force is not capable to twist the body. In order to twist the body, you will have to apply a twisting moment. Twisting moment is also known as a torque. So instead of the force, we are going to consider torque here. Instead of force, we are going to replace the force with the torque, and we are going to replace the deformation d delta in terms of the d theta. So these are the changes which you need to consider, which are represented in this diagram. As you can see, the body is rotated with the application of the T twisting moment, and due to the application of the twisting moment, this body will twist and angular deformation will occur. Now this angular deformation is again represented by the d delta, but it can be represented by d theta, because in our derivation we have used the notation as a d theta. Okay, so you can write over here d theta instead of the d delta. Then du can be calculated as the area under the d delta diagram. Okay, so we will see the similar calculation over here. A rod of the length t l, for which we are going to calculate the du, which is also one type of the triangular area, and for triangle we can write the value of the du by 1 by 2 base into altitude, that is base as a d theta. As I said, you can write d theta instead of the d delta, and height as a t. So if you put these values of d theta into above equation, then you will be able to solve the answer. So how can we calculate the answer of the d theta? Now we know the one equation of the torsion, that is T by J equals to G theta upon L. Now in this equation, if you make it theta as a subject, then your RHS will look like a TL upon Gj. Now in the case of the small deformation or small length, that is dx. In the case of the small length dx, now we are going to put the value of L as a dx. So for small length, deflection or the angular deformation will also be small. So you can write d theta instead of the theta. So for small length, we have written d theta instead of theta. So this is our final equation of d theta, which will be inserted in the equation number 1 or equation number d, and finally we are going to calculate the value of the du. After simplification, you will get this answer t square dx upon 2gj, which is similar to the previous calculation of for the axial load. Now the total strain energy can be calculated by simply integrating the above equation from 0 to L. So if you integrate the above equation from 0 to L, then you will be able to calculate the total strain energy for the torsional load. So this was the second type of the load. First one was the axial, second one was the torsional. Now similarly you know the method how to calculate the strain energy for different types of the load. So I am going to just give you the final answer of the bending moment. You can replace simply the t square by m square dx upon 2gj. Now instead of g, you can simply write the equation in terms of the e, and instead of j, you can write the value of I. So this was the third type of the load which you need to consider while remembering this type of a theory of the strain energy for the different load. So now we conclude our lecture over here. Thank you.